It's 1 o'clock now. I'll keep an eye on the attendees, and I might skip back slightly if we see a load more join, but for now I'm going to get started. So today is lecture 19. Obviously we didn't have one on Friday since it was the Maybank holiday VE day. So today we've got lecture 19. On Friday we'll have lecture 20, the final lecture. But today we're going to be talking about semiconductor memories. Ziran's rejoining. Right, yeah. So today we're going to be talking about semiconductor memories. So you'll probably remember in our timing lectures and our sequential lectures, we talked about how there's two types of static memory. You've got your regenerative cell, and then you either cut the feedback loop or you overpower it. We saw that cutting the feedback loop is what makes our standard flip-flops that we use all over our processor. And then we heard about the possibility of cutting the feedback loop. And then we also heard that there is dynamic memories, which work on the same principle as dynamic logic in terms of the value being stored on the parasitic capacitance at a particular node. So today we're going to be looking at the static overpowering technique and the dynamic memory technique. So first thing, an overview of semiconductor memories, because we've got quite a few different classifications of them. So we've got read-write memory, read-write memory. So that is memory that you can both read from and write to. We've got non-volatile read-write memory. So this is memory that you can read from, write to, and also is non-volatile. So when you power your chip off, it doesn't lose its state. Whatever you've written to the memory stays there, and when you power your chip back on, it'll be available for you. And then we've got read-only memory, right? So these are the three most basic classifications of memory. What about write-only memory? Is write-only memory a thing? Do we want it? Do we need it? Why not? If we can only write to it, but we can't read from it, what use is it to us? No. So a disk is read-write memory. It's a form of read-write memory. It's not, like, whether you can call it, well, it's not semiconductor memory normally, unless you consider flash storage as well. So that is where your SSD sits. You could also call magnetic storage, which is what a spinning hard drive is, a form of non-volatile read-write memory. Write-only memory, on the other hand, has a problem. We can write to it, but we can't read from it, so we don't know what we put in there. So we never get write-only memory. We can have read-only memory, where a value is in there in the first place, and then we can just read from it. We can have read-write memory, but write-only memory, because we can't read the data we stored there, is useless to us. Yes, Ziran.
Oh yeah, you just answered it. I'm thinking it's because if you can't read it, there's no point for you to write it, right?
Yeah, exactly. Right. Saying that, there are some weird types of memory which you write one value into them and then they'll cut, and that will change some form of state. So sometimes you do have it, but it's a very, very rare, like, for example, one example of it, which is very, very obscure, if you've got a serial port, you might write the baud rate to it. There's no point reading the baud rate, you already know what the baud rate is, but you might write the baud rate, for example. So configuration sometimes will be write-only, but that's a very, very specific thing, and it's not really a memory at that point. But yeah, generally we don't have write-only memories because they're useless to us. So we've got these three forms. Under read-write memory, we have two forms, random access and non-random access. Right? Random access means that if you've got a block of memory here, you can access any point in the memory in any order as you like. Whereas with non-random access, there is a specific access pattern that you have to follow when you read it, etc. So for the random access, so that's our general RAM, random access memory. So this is random. This one is access. So that's, you got your static random access memory and you've got your dynamic random access memory. So DDR3, DDR, so it stands for double data rate version. And then if we take DDR4, that's actually not the full name of it. So DDR4 is actually, people have forgotten to put DRAM on the end of it. So yes, it's actually a form of DRAM. So this is your DDR 1, 2, 3, and 4. There's also a form of DRAM called SDR, single data rate. And then you've got all other variations of it. But the individual cells on the memory are all the same style. It's just a matter of the exact input and output specification with that. For the non-random access, the easiest example is a FIFO or a LIFO. So if you imagine you've got a block of memory, you put data in this end, it comes out of this end. If you put data items 3, 6, 14 in there, can't really read that 6 unfortunately, 6, then they'll come out as 3, 6, 14, right? First in, first out. So that's FIFO. You would also know this as a queue. Alternatively, LIFO, which is a stack, if you put the data items in the order 3, 6, 14, then you'll get 14, 6, 3 come out the other end. So they come out in the reverse order. That's a LIFO. Notice you can't just access any element of the memory, you have to read them out in order, so it's non-random access. A shift register is basically just a FIFO, but you can't tell it when you want data out. Data goes in on every clock cycle, and data comes out on every clock cycle with a shift register. CAM, or content addressable memory, is a bit of an odd one. It's sort of halfway between the two in that you can access it somewhat randomly, but you can't tell it where to access it, right? With a content addressable memory, we use these for caches. So we say, okay, I want data item 0x3f, for example, so hexadecimal 3f, I want that data item. It will look up in its table, where is 0x3f, right? So this will be stored in there, and then it adds something called a key, and then that will have a value associated associated with it. Let's say 0x3b, for example. Right, so it'll look up 0x3f in its memory, which is something that's stored in there, and then it'll look up the corresponding value associated with that, right? The key point here is that if you then try and look up 0x, data item 0x1a, 0x1a might be down here, right? It won't be, it's not a offset in the memory, it's an actual data item that you are looking up, right? As a key, and then it returns the corresponding value. Maybe 0x1a has a value of 0x0 associated with it. Okay, so it's a key value storage, and so you can't just randomly access it. You need to know an item that is in the content addressable memory and then query the corresponding value, right? Over on the non-volatile side, so all these types of systems, SRAM, DRAM, and then the FIFOs, LIFOs, shift registers, and CAMs are all forms of volatile read-write memory. When you turn the power off, they die. There's nothing left. The data gets removed. Do we consider a parallel access shift register as a non-random access as well? So when you've got parallel access so that you can read out the entire data at once, if you add on a multiplexer and then have some select lines on the shift register so that you can read any one bit from the shift register that you want, then yes, it becomes random access. If not, just being able to read your entire data structure at once doesn't really count as random access. You could call it full access or something like that, but it's not random in the sense that you can't randomly select one chunk of it. Okay, so you would need some form of multiplexer so that you could select different sections of your shift register. So the reason that doesn't, so someone said if we turn off the computer for a very long time, the data saved in SSD might be lost. That is true in a way. Each SSD has its own battery on it, which keeps the NAND flash in a sensible state, so it doesn't actually decay for multiple years. But yes, theoretically, it could eventually disappear. So flash is a bit of an iffy one. It has a lifetime of like several months, so 6 months to like maybe 2 years, right? Lifetime, due to the fact that it has a battery on it. If you have a very small amount of power for a very short time, that will recharge the battery, so you really don't need to worry about it. You can consider it a non-volatile form of storage, unless you're looking into archiving, at which point just go straight for the magnetic storage anyway, because flash isn't good for archiving. Okay, but yeah, for our intents and purposes, flash is non-volatile. Looking at the other ones, we have EEPROM, so that's erasable programmable read-only memory. So we erase it with a UV light. We then program it with, so this is a write once memory. So we erase it with a UV light, we then get to write to it one time, and then it becomes a read-only memory. Right? So question, isn't that cheating though? If you apply your battery to any of these technologies, they become non-volatile. Yeah, as I said, it's a matter of perspective. So with a simple coin cell battery, flash will live years and years and years. In fact, you could probably get it up to oh, what happened there? You could get it up to maybe 10 years with a high quality coin cell. If you look at DRAM on the other hand, you've literally got maybe 3 weeks max if you keep it only refreshing at the very lowest rate and you don't access it at all. But 3 weeks is quite a generous estimate. 3 weeks, right? Maybe a month, right? So it's all a matter of scale, and like flash, at the end of the day, when you turn your device off, your processor powers down, and it powers down your DRAM anyway. Flash, obviously it doesn't power it down. Is the hardware on the left hand side generally more expensive than the right hand side ones? Not to a certain extent. I'll go into cost in a moment. Okay. Just finish off the last few here. This one is electrically erasable. So you use a very high voltage to erase the cell, and then a lower voltage to write to it, and then it's programmable ROM. Then we have just normal PROM, so there's no UV light to erase this stuff, so it's a read-only memory because this one is a write once. And then we've also got mask programs ROM, which is literally just a set of wires either connected to VDD or to ground. So you've got a set of wires like that. That would output 1010, where that's connected to VDD, that's connected down to ground. So mask programs ROM, right? So we've got all these different styles of RAM, of memory. We're focusing on SRAM and DRAM, right? So looking at, so now we're going to look at something called the memory hierarchy. Basically, a fast memory is very, very expensive, right? So this is your sort of, your flip-flops and your SRAM over here. Right, flip-flops are actually more expensive than SRAM. Your standard SRAM. It's very, very fast, so 100 picosecond time. But because it takes up so much area on the chip, you're going to get hundreds of bytes rather than anything bigger, right? And it's very expensive to do each byte of data, right? So we don't have much of this very small, very fast memory. Very large per cell, very fast memory, right? On the other hand, you've got very slow memory, so your non-volatile memory. It's milliseconds, microseconds to access, something quite long, but we get terabytes of data, and it's low cost per byte of data, right? So what we really want is something that's got lots of storage, like this over here, but is really fast, like this over here. But we can't have it. So what we do is we create something called a memory hierarchy, where we say we'll have a small amount of really fast memory, a large amount of really slow memory, and then a lot of different layers in between, which are progressively slower, bigger, and less costly, right? So main memory, for example, so here we've got maybe 1 terabyte disk. Here maybe we've got 16 gigabytes of DRAM. You might have maybe a 32 megabyte second level cache. You might have, say, a 32 kilobyte instruction cache and a 32 kilobyte data cache. The TLBs will be more along the lines of 1 kilobyte. So these are just for dealing with memory virtualization. And then your register file will be maybe 32 registers multiplied by 32 bits or 4 bytes. right? So that would be 64, 128 bytes, right? Would be a typical memory hierarchy. The key thing to note here is that if you've accessed data item 0xFFE86401, if you've accessed this byte in memory, then item FFE86402 and FFE86400, so we access this one item here, these items are more likely to be accessed than some other item over at 0x64021801, for example. This one is not likely to be accessed. These two, on the other hand, are very likely to be accessed. This is the principle of locality, right? Data items close to the ones we've most recently accessed and the one we've most recently accessed itself are more likely to be accessed soon. And so what we can do is we can store a chunk of data close to what we've accessed in one of these memories, and then most likely we will be able to just pick up that data very, very quickly, rather than having to go all the way back to secondary, like the largest piece of memory in our system. Most likely we'll be able to fetch the data from a much lower level cache, like the instruction cache, data cache, or a second level cache. Right. So TLB stands for Translation Look-Aside Buffer. What it does is it says, okay, given a virtual address for a particular program, that corresponds to this physical address in main memory. So if you ever see accesses in this region, look up this physical address. It's purely to do with your memory virtualization in your system. They're very small memories because they only have to, and they're a content addressable memory, and they store a certain number of entries saying, oh, this thing goes to here, this thing goes to there, this thing goes to the other, and it basically just works as a cache rather than going all the way through your page tables, which are stored in main memory. So yeah, it's just a cache for lookups in the virtual memory system. That is talking in terms of how the data is written in memories. I'm not sure what you're saying there, Joydeep, so could you explain that in a bit more detail? Right, I'll continue on, and then here we go. In terms of data is written sequentially in memories, yeah, so that's what we call an access pattern. In terms of if you're writing a for loop in your C code, less than n I plus plus, right? If you're saying, okay, x equals data of I, x equals x plus 2 data of I equals x. So if you have that instruction sequence, two things to note here. First thing, if we've read from a particular element in memory, then most likely there's a good chance that we're going to write to it later, and quite soon at that. So having it stored in one of these caches is always a good thing. But also, if we've accessed data element I, there's a good chance we're going to either go to I plus 1 or I minus 1 on the next cycle, right? So just looking at how programmers work with data, it's generally the case that if we're accessing one element of data, the next thing to be accessed will be an element next to it in memory, okay, in the virtual address space as such. So that's why we say we have a principle of locality. We want to keep similar data together, and we want to work on all the similar data at the same time, like in sequence. And that's why these caches work well. There are some algorithms which will just do what we call scattered reads and writes, in which where the next data element is completely unknown. We don't know what it'll do based on the data we've currently been reading. In those cases, these caches actually make us slightly slower, but these are rare enough algorithms that we don't care about it, okay? So as much as these will make it slightly slower, if we've got a very, very random pattern where we don't know where we're going to go next, it's rare. 90% of cases, these caches give us a speed up, so it's worth having them there, right? Even if they add extra cost to the chip. As the chips have gotten more and more advanced, we've started including both the second level cache, which is made out of SRAM, and now sometimes even the main memory, the DRAM, onto the same chip or the same package, right? So when we first had our processors, we had very, very small instruction and data caches. We had our main memory, and we had our disk. And then people started creating chips which were faster access, but smaller pieces of memory than main memory. We then said, okay, let's try incorporating them onto our processor. So now we have a 32 meg cache, second level cache built into our processor. And then more recently, when we've tried to go for an entire system on a single chip, we've started putting things like EDRAM on there, embedded DRAM, where it's all on a single package, including the main memory, and the only thing that's external is your disk, which will probably be flash memory in that case. So that's sort of the overview of how memories work. I might have to go into the next lecture for this one. What's the reason originally CPU design is not a SoC? That is purely due to process improvements. So when we first did transistors, they were big enough to physically see with the naked eye. And they've gradually gotten smaller over time, as according to Moore's law. When we first designed processors, it was actually a struggle to get a functional processor on quite a large chip, right? So we didn't have the opportunity to have lots and lots of extra components like you would see on a system on chip, like ADCs, DACs, memory controllers, virtual memory, screen controllers, USB controllers, all this extra stuff that we put on a chip nowadays. We just didn't have room for it. As the transistors have gotten smaller, we've found that we can put more on a chip, and so we've been able to put extra stuff on it, and that's why we've moved towards the system on chip style designs, because it's cheaper when we've got lots of very, very tiny transistors. It's cheaper to make an entire to make a single chip which will implement the entire system than to have 100 chips doing the same thing, right? But that's only possible because we've got the smaller transistors. And so the same thing here, we can only now incorporate the second level cache onto our chip because our transistors and our memory cells are smaller, so we've got space for it, right? And it's worth it in terms of keeping the memory as close to the physical processor as possible. So let's have a look at how we might implement one of these RAMs, because first we need to think, well, how are we going to lay out all this memory? We know how to create a single cell, let's presume. How are we going to lay it out? most simple thing that we did, and like how the original memories work, was they were 1D memory architecture. So we had a select line coming into the chip, into the memory chip, for each word of data. Right? We would set one of these select lines high, and then the entire word would be output over the data line. So this would be the data, this would be the address. So, and we would just set one of these select lines high to select a particular word. Problem with this, obviously, if you've got more than 100 bytes in your memory, you end up with more than 100 select lines, and this is just unfeasible. We can't put that many pins on our package, right? We can't have all those lines. So, instead we use something called a decoder. So if we've got k select lines, we have n words such that k is log 2 of n, or alternatively n equals 2 to the k. Right, what is a word? A word is just a logical grouping of bits in our memory, right? So here we've got a word size of m, so that's a logical grouping of m bits, which we all want output at the same time. So for the very first processors, m equals 8. So we have a word size of 8 bits, or 1 byte. Right? For the very first processors. As processors have gotten more advanced, we've said actually we want to deal with more data at one time, because we're able to do that on our processor. We've got small enough transistors that we can process 32 or 64 or 128 bits at a time, and so m has increased, and now you're more likely to see 64-bit or 128-bit words on your storage shell, right? So you're going to see more data coming out than on the old processor. But the key point here is that when select line 0 goes high, word 0, and so all the bits associated with word 0, right, all come out on the data line, right? Or conversely, you write that many bits to word 0, right? So it's just a logical grouping of bits. A pointer is simply a number that addresses a particular word in memory. So your pointer would be that thing. So if your pointer had the value 0x3f, these ones would have the values 0011, 1111, so presuming we've got an 8-bit address, and then that would go to word 3f would be 3 times 16 is 48 plus 15, 63 it would go to, right? So your pointer says 0x3f, presuming an 8-bit address. You go to word 63, I hope I calculated that right. Yeah, that should be right, yeah. In your memory, right? So a pointer is just a number which corresponds to one of the words in your memory. Okay? Problem is, even with the decoder here, right, we've got an aspect ratio, so a input to output quantity of, if we say a 20 bits, an 8-bit, how did that happen? 2 to 3, right, n is 1 meg, which is 2 to the 20, k is log 2, which is 20. Yeah, so if we have, say, a 20-bit address, we get an aspect ratio of 2 to the 20 by 2 to the 3, right, which is 128,000. That means we've got 128,000 words all being worked off of this one decoder. that sort of aspect ratio isn't possible for us to create a decoder like that. We can't have a decoder with 128,000 outputs. So once you start getting up to 20-bit addresses, suddenly you start need to thinking, okay, maybe a 1D memory architecture isn't correct. We need something a bit more advanced. So we create a 2D memory architecture. Rather than just having a single row decoder and then all the bits from that row being output at once, we have a row decoder which selects a row of our memory, and we have a column decoder which selects a column of our memory, and then at one particular row column location we will have our M bits, right? So if we've got a 20-bit address, for example, we might have 4096 word lines, so 12 bits here. We might have 256 of the words per word line, so 8-bit address. And then this, we will have 8 bits, because we assume M is 8 bits here, multiplied by our 2 to the 8, so which is 256 words per word line, which is 2 to the 11, which equals 2048 bits here, and then those and then this will select one group of 8 bits, so we'll have 8 bits coming out here, and then through the sense amplifiers and read-write circuits. So notice how what we've done is we've split our row decoder that we found here with a 20-bit address into a row decoder and a column decoder with a 12-bit address and an 8-bit address. The row decoder enables one row of memory. The column decoder connects one of those rows of one of those columns in that row to the sense amplifiers and the read-write circuits, and therefore allows you to work with that one cell, which is maybe 8 bits or it could be 32 bits long. Right? Yes, Saran.
I don't get it. Why is not 2 in power of 8 multiplied by the 2 in power of 12? Can you explain the math again?
Right, so specifically, if you're talking about this one here, I presume that's the one you're talking about?
Yeah.
Right, so I'm talking about the number of bits coming out to the bottom of this memory, okay? So the point is that each one of these rows in the same column, so each cell in this column, they're all connected up to the same single wire, right? Every single cell in the column is connected to the same wire. The row decoder just enables one of the cells in this column, right? So only one of them is ends up actually driving that wire, or being driven by that wire. And then the column decoder selects a group of 8 wires to actually be used by the sense amplifiers and the read-write circuits. Okay, so we've got down here we've got however many words are in each row, which is 256 because we've got an 8-bit column decoder. And then we have to multiply that by the number of bits in each word, which is 8 bits. So we get 8 bits, that's the number of bits per word, multiplied by the number of columns that we've got in our memory, which is 2 to the 8, which is 256. Therefore, we end up with 2048 wires coming down here, right? The other 12 bits of our address is encoded in the row, and only one of these rows will be enabled at any one time, okay? So that's what gates off the other 12 bits of our address. Does that answer?
In each column, you have 2 in power of 8 entries, and in each entries, you have 8 bits, which is a word.
So in each column, you have 2 to the 12 entries in each column. In each row, you have 2 to the 8 entries, right? then your row decoder only enables one of the 2 to the 12 items in each column. And then your column decoder selects one of those 2 to the 8 entries.
So totally you have 2 in power of 8 multiplied by 2 in power of 12 entries.
Yes, in your entire 2D memory. So this is
Yeah.
2 to the 8.
So the
This,
width multiplied by height.
yes, is 2 to the 12. So you have 2 to the 20 entries in your memory, but the row decoder only activates 2 to the 8 of them, which is one row, and then your column decoder selects one item out of that 2 to the 8. Does that make sense?
Yes. Thank you.
Yep. Brilliant. Right. Okay. So we've got a 2D memory architecture, and that works fine. And then we get up to multiple gigabytes of RAM, where we've got greater than 32-bit addresses, or sometimes even with just 32-bit addresses if you want fast memory. You realize, hang on, wait a sec, we've now got a very, very large row or column address. That's not going to work. We've got at least like 18 bits here and maybe 14 bits here. It's really getting too big for us again. We've still got a massive aspect ratio, and so we say, okay, let's just increase the number of dimensions again. So we have a block address which enables one of the blocks of memory. Then we have a row address which enables a particular row in that memory, and we have a column address which selects one of those columns, right? And so we can just increase the number of dimensions on our memory again, so that we reduce the aspect ratio, right? And we can keep doing this. So eventually, when we get multiple terabytes of memory, we'll actually end up with 4D memory architectures where we've got a block, a column, a row, and maybe a bank or something like that of memory that we activate at any one time. So yeah, we can keep expanding the number of dimensions as our aspect ratio gets too big for us to manufacture. Yes.
Oh, why not just lay multiple decoders on top of each other? Does that make sense?
Why not lay multiple decoders on top of each other? So what you're saying is having like another decoder here. Is this to just and you have like one bit selecting between the two decoders, and
Yes.
yeah, basically that's what the block address does. So if you just have two blocks, for example, you could have two decoders, each one selecting every other line, right? So that's decoder 2 there, and this is decoder 1, decoder 1, decoder 2, decoder 1, decoder 2. Oops. Right? So if we just say a 1-bit block address, we can have the two different decoders working on every other line, and then that reduces the aspect ratio by a factor of 2, right? So that's exactly what block addresses are doing. So notice how we've got separate row decoders for each block, right? And then depending on which block we select, one of the decoders will be enabled, right? And similarly, one of the column decoders will be enabled. Okay? Right. So advantages of doing this, obviously your word and bit lines become shorter, as well as obviously the aspect ratio of your decoder, and also because we're only activating one of our memory blocks, that will also save power if we do that, rather than activating a large number of columns at once. We split the memory up, so we activate less columns at a time. The one disadvantage of this, though, is that it's slower. So if we look back to our very simple 1D memory architecture where we just have select lines, there's very little logic between us enabling a select line and the input and output, right? As we increase the number of dimensions to our memory and increase the number of decoders and extra circuitry, the path through the logic becomes worse, right? It becomes slower memory, right? So this is quite a problem. As we increase the number of dimensions, because we've got more layers of logic between the actual memory cell and our data and our address lines, it becomes the case that the memory gets slower. So we need to consider, well, at what is the appropriate number of dimensions for our memory, and then this goes back to our caches and all that in terms of we can have lower dimensional memory close to the processor with smaller amounts of it, and hence it's going to be faster, and then we can have memory with higher dimensions further away from the processor where we can accept the delay on it. Memory has timing, just as we saw with our flip-flops. So we have, if we look at the write cycles for a moment, we have a setup, TSU, and we have a hold, TH. Same thing as with our as with any other type of memory. It's just a matter of we need our data valid before the setup time, and we need it to stay valid until after the hold time. Otherwise, our memory might do something weird, right? The read access time could also be known as the TCQ, right? So the time from enabling the read to the read becoming valid. So that's the same as your TCQ component with your flip-flops. Also, the time from us asserting a read to the read becoming invalid, that's your TCD memory, your contamination delay of your memory, right? So it's got exactly the same timing parameters as we saw with the rest of our with the flip-flops. It's just defined to be slightly different in terms of we need a read and a write signal instead of just a clock, because the circuit is different, the values are going to be different, but it's basically the same thing. So if we look at a small 4x4 SRAM memory, we'll look at the SRAM cell in a moment, right? We've got our row decoder we saw earlier, we've got our column decoder that we saw before, and we have two things called bit lines, right? The column decoder connects the bit line and the knotted bit line, connects the bit line up to the cell, right, and sets the bit lines the bit line knot and the bit line appropriately so that it can either read to or write read from or write to a cell, right? So the job of the column decoder is to set up the bit lines correctly from our write circuitry, right? And the address of the column decoder tells it which column to put that data onto, right? The row decoder just enables one of the cells on a column. So in this case, maybe it's enabled that one, or actually no, specifically they're saying it's enabled this cell here, right? So the actual SRAM cell, remember we saw that the best way to do an SRAM cell, like the most transistor efficient way, is to have two cross-coupled transistors, and that will give us our bistable circuit. What does the sense amp do? I'm going to get to that in a moment, okay? So just bear with me for what the sense amp does. The sense amplifier is down here. It's this component here. I will describe it in a moment. Right. So with the two cross-coupled inverters, so that's one inverter there and one inverter there, gives us our bistability. And then we have two pass transistors here and here, and the job of these pass transistors is to enable the data to flow in and out of the cell, and just to allow us to overpower the feedback loop, right? So first thing, we're going to look at what happens if we read. So we'll assume that a 1 is stored in the cell. So Q is 1 and Q naught is 0, right? Based on the fact that Q is 1, we know that this NMOS must be on, and since Q naught is 0, this PMOS will be on. Obviously, there is an open circuit just here, and an open circuit just here, so this is the corresponding NMOS and PMOS, but they're turned off, right? So we don't have to worry about them, not there actually, right? Going up to VDD and down to ground. Point is, they're open circuits because of the value stored, right? So let's look at what happens when we read. We pre-charge both the knotted bit line and the bit line to 1. Our bit line, because we're storing a 1 inside our cell, this PMOS stays on, and bit line stays at 1. On the other hand, the knotted bit line, because we've got a 0 on not Q, and we've got a 1 over here, this NMOS is on, so this will transition from a 1 to a 0. We'll discharge the knotted bit line down to 0. So we'll end up with a 0 on BL naught and a 1 on BL, and so we've got our value out, right? If, on the other hand, we were storing a 0, this one would transition to a 0, this one would stay as a 1, and so we'd end up with 1, 0. So we can see that we've got our data out, regardless of whether we get our 1 or a 0, right? Problem is, we've got this problem called read upsetting, or read disturbing. As this NMOS discharges C bit, so discharges the knotted bit line, the voltage at this thing will rise up slightly as charge is redistributed between C bit and the capacitance at this point, right? This will rise up slightly. If this rises too high, this will cause M4 to turn off, and I believe that's M3 to turn on. Yeah, M3 to turn on, and so it will change the value in our cell. So we need to be very, very careful that this does not rise above V mid, our crossover point, right? So we need to be very, very careful about that, and we need to size M1 and M5 accordingly, right? So what we do is we define something called a cell ratio, which is the width of M1 by the length of M1, divided by the width of M5 divided by the length of M5, right? So it basically says it's the width by length ratio of M1 divided by the width by length of M5. If M1 is bigger than M5, what's going to happen is we're going to have, obviously, a potential divider between these 2 points. There's our ground, and this one is currently charged up to VDD, and we're looking at this point here. If the resistance across M1 is low enough compared to M5, or in other words, M1 is a wide, short transistor and M5 is a narrow, long transistor, then this point here will never cross the midpoint. and therefore we know we won't read upset, right? On the other hand, if M5 is a wide short transistor, so it's a powerful transistor, and M1 is a narrow long transistor, so it's a weak transistor, then the Q naught point will rise above V mid and will read upset, right? So if we assume that the transition point is 0.5 volts and we've got a VDD of 2.5 volts, we see that we need a cell ratio of about 1.2 for one specific process to ensure that the voltage rise on Q is below the threshold on an NMOS, right? Which is a good point to look at when deciding, right? So we'll see that most memories will have a cell ratio greater than 1.2, right? Normally it's in the region of 1.25 to 2, just to make sure. How are we for time? I'll quickly go over the right, but I might finish this off next lecture, and then we'll see how we get through next lecture, and I might do another one just to finish it off. So looking at the right, this time we pre-charge B. We've got a 1 in our cell. We're going to charge BL0 to 1 and BL to 0, and we're going to keep providing charge to these so that we make sure that we can, or I should probably draw that the other way around. We're going to keep providing charge to these so that they can definitely overwrite the cell. And once again, we're going to say, okay, we've got our M5 and our M1 and our M4 and our M6 enabled because we've got a 1 stored. Obviously, in order to avoid a read disturb, we know that M1 is stronger than M5 because it has to be in order to avoid the read disturb. So there's no way for this to force a 1 onto this node here, right? That can't happen. So what we need is we need for M6 to overpower M4, right? So we define the pull-up ratio to be the width by L of M4 divided by the width by L of M6. Width by length, should I say. And then we say as long as our pull-up ratio is high enough, we can overwrite this one here with a 0, thereby turning off this one and turning on M2, right? And therefore that M2 will then pull this up to 1 and M1 is off. M1 is off, meaning that it's no longer pulling down, right? So we're trying to write to the cell using the pass transistors overpowering the pull-up transistors, right? This is a trivial matter due to the fact this is a PMOS transistor. Because the PMOS transistors have a lower electron hole mobility, they have a higher on resistance for the same size. Merely having a minimal sizing on both M4 and M6 is sufficient for M6 to overpower M4 because M6 is an NMOS driving a 0, whereas M4 is a PMOS of the same size, hence higher resistance, driving a 1, right? So our bit line and our M6 will overpower M4, transition this 1 to a 0, and then that writes to our cell. The pull-up ratio normally needs to be above about 1.5 in order to, or maybe 1.6, so pull-up ratio greater than 1.6 in order to make sure that we have a, that we actually write to the cell, that we get above our absolute magnitude of the threshold of the PMOS transistor. Where did I go? There. So we need to get greater than a 1.6 pull-up ratio. But if we look at, say, our 0.35 micrometer hit kit, if we have minimum NMOS and a minimum PMOS, our pull-up ratio is already about 2.3, just due to the difference in electron hole mobility. So we've easily satisfied the pull-up ratio requirement for our cell. Okay, purely due to the fact that the PMOS has a lower electron hole mobility. Okay, so generally you can say that M4 is going to be 4 lambda by 2 lambda, so absolutely minimum sized. M6, I'm just going to say M2 equals M4, which is going to be 4 lambda by 2 lambda. M5, so equals M6, so these are the two pass transistors, and they can also be minimum sized. And then the last two is M1 and M3, right? These ones need to be slightly bigger. They need to be at least 1.2 times. So we're going to say, 1.2, if we say take our 4 lambda and we multiply it by 1.25, that gives us a nice easy value of 5 lambda by 2 lambda. So our M1 and our M3 will be slightly bigger at 5 lambda by 2 lambda, giving us a 1.25 ratio. And then M2, M4, M5 and M6 will all be absolutely minimum sized. And that will give us a working memory, right? And then we can adjust those ratios to get slightly better performance if we want, right? So that's how you would do it with an SRAM cell. So that was looking at a 4x4 SRAM memory. Next time, I think, we shall look at a 4x4 DRAM memory, and we'll see the minor differences that occur with DRAM. Okay? But that will be for next lecture, and then depending on how we go, I might have another to finish it off. In the next lecture, could you maybe talk a bit about FinFETs as well? We have studied planar fabrication and design, but the industry is moved towards FinFET technology. Just a bit of information about it with regards to layout and design considerations, as well as benefits and advantages. Yeah, I'll have a look at some details on FinFET and talk about it a little bit. Unfortunately, the HitKit process isn't anywhere near FinFET, but I'll have a look up, give it a look up, and I'll give just like a vague overview of what FinFET's all about anyway. So yes, I will do that. Okay. Yep, right. Is there any questions that we've got for today? No? Okay. In that case, I will leave it here for today. Next lecture is on the 15th of May, where we will be finishing off the DRAM lectures. That's only 4 slides, luckily. And then we'll be starting on... I switch over to it. Oh, open folders, lectures. And then we'll be starting on sequential dynamic logic, right? So this is the fully dynamic section, the fully sequential section of dynamic, not just the tiny bit of charge storing on internal nodes. But that's a relatively simple part of it. Okay, so that's what we'll be doing next lecture. I'll see you then.